All fuel-injected Yamaha motorcycle, ATV, scooter, snowmobile, and side-by-side models since 2002 have a self-diagnostic system to check operation of many of the fuel injection circuits and components. This system is built into the ECU and has two modes, normal and diagnostic, which is called Diag in all service literature. Normal mode continually monitors the fuel injection system for problems, and if there is some type of FI failure, the ECU will either not allow engine operation, or in some cases will go into a pre-programmed default fuel injection map to allow the engine to continue to operate. When the main switch is first turned on, the normal mode checks the FI circuits and sensors that operate without needing the engine running. If a problem is detected, the ECU will illuminate the check engine light if the unit has one. And if the unit has an LCD display on the meter assembly, a fault code number will be displayed. The fault code number is referenced in the service manual, which will tell you which component or circuit is affected. If the ECU has a default map programmed for that particular circuit, then the unit can be started and possibly driven. I say possibly driven because in some cases engine performance in this default map could be poor. It's usually a very rich air-fuel ratio. For example, the ECU has only one sensor for engine coolant temperature. If there's a complete failure in the temperature sensor or circuit, the ECU has no idea what the engine temperature really is. So the default map in this case will use the coldest temperature setting in the programmed range, which is around -20 degrees, which will result in a very rich air-fuel ratio. If the particular failure is in one of the major circuits that are absolutely necessary for engine or fuel injection operation, or a safety-related circuit, the ECU cannot use a default map for these failures. At that point, the ECU will not allow the engine to start, and the check engine light will flash when the starter button is pushed when trying to start the engine. If the ECU does not detect a problem when the key is first turned on, it then waits for the engine to start and then checks the remainder of the fuel injection circuits. While the engine is running, the self-diagnostic mode is also continuously in operation, monitoring the fuel injection circuits. If one of the major components or safety-related circuits has a failure during operation, then the ECU will illuminate the check engine light, again continuous on, not flashing, and shut the engine off. The corresponding fault code number will be displayed if the unit has some type of LCD panel in the meter assembly. There are some cases where you must turn the main switch off and then back on, or try to restart the engine to display the fault code number. If the unit does not have an LCD panel, but does have a check engine light, such as the Zuma 125 and C3 scooters and older Raptor 700 ATVs, the check engine light will display a series of flashes that indicate the fault code number. But the FI diagnostic tool is really the best method to see the fault code number. During operation, if the ECU detects a failure in one of the non-critical sensors, such as air temperature, the check engine light will illuminate, also continuous on, not flashing. And the ECU will go into the pre-programmed default map for that circuit. Usually the engine is allowed to stay running, but as we mentioned, in many cases, engine performance and possibly throttle response will be affected. The fault code number for this type of failure is usually displayed on the LCD panel. And again, you might need to turn the main switch off and then back on to display the fault code number. If there are multiple fault codes, meaning more than one circuit or component has had a failure, then the fault codes for each failure are displayed in numeric order at 2-second intervals, and the sequence repeats as long as the main switch is on. The other main function of the self-diagnostic system is the Diag mode. The Diag mode has the ability to display the readings or output from the various fuel injection and safety-related circuits as they are going into or processed by the ECU. To access the Diag mode on most models, you press and hold both the select and reset buttons on the meter assembly and then turn the main switch on. Keep the buttons pressed for about 8 seconds and Diag will appear. Now release the buttons and then press both buttons again. The display will show the first Diag code, which is D01 or D101 on some models. This is the Diagnostic Code 1, which happens to be for the TPS, the throttle position sensor. The procedure is slightly different on some models, like the Rhino and Roadliner and Stratoliners, and some models do not have an LCD panel in the meter assembly. Be sure to check the owner's or service manual for the exact procedure. In Diag mode, the engine will crank over but will not start. This allows you to check the operation of certain systems, such as the intake air pressure sensor, for example. The reading should fluctuate as the piston is going up and down in the cylinder. Here's a very important point you must keep in mind when troubleshooting a Yamaha fuel injection system or running performance problem. For most fuel injection circuits, the ECU is checking for an open or short circuit. It does not check if the actual reading coming from the sensor seems correct or not. Take the coolant temperature sensor, for example. There's only one, like we mentioned. If the ECU is getting a reading from that sensor, any temperature reading in the programmed range for that sensor, which is around -20 degrees to over 240 degrees, then the ECU must believe that temperature is correct. If the coolant temperature sensor or wiring has some failure, causing the temperature reading to be very low, then the ECU has no choice but to believe that reading and possibly set the fuel injection to startup mode, which would be a very rich air-fuel ratio. Diag mode allows you to quickly check many fuel injection sensors and wiring, and you can also activate many fuel injection related components, such as the fuel injectors, ignition coils, cooling fan, and other electrical circuits, even on a unit that won't start. Set the unit into Diag mode and refer to the fuel injection section of the service manual. The first Diag code, D01, is for the TPS, as we mentioned. You see the display will show you the throttle plate angle that the ECU has calculated from the sensor voltage, measured in degrees, as you open and close the throttle. As you go through the different Diag codes, you will see just numbers, without any notation that it's an angle or voltage or degrees of temperature, etc. This is where you have to learn what those numbers represent to quickly verify if that circuit is working and if the readings are correct or not. Here's a good example. Diagnostic code number 5 is the intake air temperature, and number 6 is the coolant temperature on liquid-cooled engines. When you display those codes on a meter, you will see the actual temperature that the ECU has calculated from the sensor voltage. Now the only tricky part is that some models are in Fahrenheit and some are in Celsius. And unfortunately, there's no indication in the Diag mode or note in the service manual as to which scale it's in. But there is a handy chart available in the Yamaha Fuel Injection Systems book that lists which models are in Fahrenheit and which are in Celsius. This chart also shows which FI sensors and other systems are on all fuel-injected motorcycle, scooter, ATV, and side-by-side models since 2002. This is a useful chart to refer to when you're troubleshooting a unit to know which sensors and systems a model has. Going through the Diag mode whenever you're working on a possible fuel injection system or running performance problem is a great habit to get into. Once you learn what all the numbers mean, it only takes a very few minutes to locate a possible cause or eliminate a huge amount of work checking each sensor and wiring. The Yamaha Fuel Injection Systems book contains a handy list of all current Diag codes and explains how to check each code, what the numbers mean, and how to interpret the information. Here's the logical steps of fuel injection troubleshooting. First, see if there are any fault codes in the system. Follow the steps in the appropriate service manual in this video to troubleshoot any problems. Next, if no fault codes are present, go through the Diag mode for clues. The diagnostic system is mainly looking for an open or a short in many of the sensor circuits. Like we said, as long as the ECU is getting any reading within the operating range of the particular sensor, it will not activate a fault code. This doesn't mean that the sensor is operating correctly. It could be sending totally wrong information to the ECU, and the ECU would then be incorrectly setting the air-fuel ratio, resulting in poor performance. So looking through the Diag mode for readings that are incorrect is vital to quickly and accurately diagnosing a performance complaint. If there are no fault codes and no obviously wrong readings in the Diag mode, all fuel injection troubleshooting should start with the fuel pump system. Keep in mind there is no fuel pressure sensor, and all fuel injection calculations are based on the set fuel pressure for that model. The engineer who designed that model relies on the fuel pressure always being to the set spec, so all he has to do is determine when and how long to energize the fuel injector to get the desired air-fuel ratio. A couple of tips to keep in mind on fuel pressure testing. Be sure to bleed off the fuel pressure by disconnecting the electrical lead to the fuel pump and running the engine until it will not restart before disconnecting the fuel hose, and keep a rag handy. After connecting the fuel pressure gauge, turn on the main switch. All Yamaha ECUs activate the fuel system relay for 4 seconds when the main switch is first turned on. This builds up the static fuel pressure in the system, getting ready to start. Then, when you push the starter button, the ECU activates the fuel system relay to supply battery voltage to the fuel pump and fuel injectors. So when the main switch is turned on, you should see the fuel pressure quickly build up to the specification and hold there for at least several minutes. A low pressure reading may be caused by a weak pump, blockage in the fuel line, clogged inlet filter, a faulty pressure regulator, or low voltage to the pump. On return type fuel systems, the pressure regulator is an external device. The regulator is basically a spring-loaded valve which is mechanically set to maintain the desired fuel pressure at the injectors, and any fuel that's not used is returned to the fuel tank. To quickly test if a low fuel pressure reading is caused by a faulty regulator or something on the pump side, find the fuel return hose and pinch it closed for just a second. Be sure to only pinch the hose for just a second. Do not clamp the hose with some type of clamp or locking pliers. The fuel pressure should quickly spike within the maximum fuel pump output range. If the pressure does come up to the correct pump output range, then we know the pump is good and the low fuel pressure will be caused by a faulty pressure regulator. But if the fuel pressure does not come up to the correct pump output, then the fuel pump itself might be bad, or again, there could be a blockage in the fuel line, clogged inlet filter, or low voltage to the pump. On returnless systems, the pressure regulator is an integral part of the fuel pump itself and cannot be replaced separately. So if the fuel pressure is low, check for blockage in the fuel line, clogged inlet strainer, or low voltage before replacing the pump. Some returnless systems have a pulsation damper attached to the fuel rail, which evens out the pressure fluctuations caused by the opening and closing of the fuel injectors. They're very simple to test. First, if there's any sign of fuel leakage, then the internal diaphragm may be damaged. If there is no sign of fuel leakage, bleed off the fuel pressure by disconnecting the electrical lead to the fuel pump, start the engine, and let it idle until it dies. Then reconnect the electrical lead to the fuel pump and turn on the main switch. The center plunger in the pulsation damper should extend a few millimeters as the pressure builds back up in the fuel rail. For a no-start problem, checking for battery voltage going to the fuel injectors is an important step. But remember that the voltage is coming from the fuel system relay, and it's only activated for 4 seconds each time the main switch is turned on. So as you're checking for battery voltage at each injector with the main switch on, remember that the voltage is turned off after 4 seconds. If you check for voltage after this time, you could misdiagnose a problem with the injector wiring or fuel pump relay circuit. Keep in mind as we discuss some of the following electrical checks that the wire color codes mentioned here are very common on many models, but not all. Be sure to check the service manual for the proper color codes and specs when you're working on a particular model. As far as troubleshooting the fuel injection sensors go, we've got two main groups: sensors with 2 wires and sensors with 3 wires. The throttle position sensor and accelerator position sensor used on Yamaha chip-controlled throttle or YCCT models have 4 wires. We'll discuss those in just a minute. Temperature sensors, air, coolant, engine, and oil, all fall in the 2-wire group. These sensors all function the same way. They're connected to the ECU in series on a 5-volt DC circuit. The 5-volt positive side is usually a unique color code wire, such as brown with a white trace for air temperature and green with a white trace for coolant temperature. And the ground side of the circuit is a black with a blue trace wire, which is the common fuel injection sensor ground circuit on many models. These temperature sensors change their internal resistance based on the temperature of what they're reading, the coolant or cylinder head, or air or engine oil. The ECU monitors the voltage in each temperature circuit and converts that voltage to a temperature reading. A static resistance check is usually the most efficient test of these sensors. Check the appropriate service manual for the specs. But one thing the manual doesn't mention is testing the voltage. Disconnect the sensor and check voltage at the connector. With the main switch on, you should read at least 4.7 up to 5 volts DC on the connection. Another 2-wire sensor is the crank position sensor, which produces a low AC voltage as the engine rotates. It's very easy to check this sensor with the ignition mate or a peak reading volt-ohm meter set to AC volts. Make a parallel connection to the 2 wires and start or crank the engine. Most all crank position sensors generate about 1 to 3 volts AC at cranking and about 8 to 9 volts at idle. And finally, the O2 sensor is considered a 2-wire sensor for troubleshooting. Currently, Yamaha only uses the narrow band O2 sensor. And even though some have 4 wires, only 2 of the wires are for the O2 sensor. The other 2 are for the internal heater on some models. O2 sensors are used to determine if the air-fuel ratio is too rich or too lean by measuring the amount of oxygen left in the exhaust gases after combustion. When a narrowband O2 sensor is at its operating temperature, it detects the oxygen content of the exhaust and through a chemical reaction generates a small voltage, up to a maximum of 1 volt DC. The ECU has instructions in its memory for what conditions to include the output voltage from the O2 sensor in the fuel injection calculations. These are the different maps for closed-loop operation that we mentioned in the first part of this video. So even though the O2 sensor is always generating that voltage, the ECU only considers that information when it's in closed-loop mode. All other times, the ECU ignores the O2 sensor voltage. The ECU is looking for the output voltage to be right at 0.45 volts DC, which is the output voltage from a narrowband O2 sensor when the air-fuel ratio is at 14.7 parts of air to 1 part of gasoline. A 14.7 to 1 ratio is referred to as a stoichiometric air-fuel ratio, which loosely translated means a chemically balanced air-fuel mixture. A stoichiometric air-fuel mixture should have just enough air to support the complete burning of all available fuel, which would be nearly perfect combustion, a point at which the catalytic converter is working most efficiently. But a stoichiometric mixture burns very hot and can damage engine components if the engine is placed under high load with this air-fuel mixture. So the ECU only goes into closed-loop mode at times when the engine load is very light, idle and steady throttle cruising speeds on most models. When the O2 sensor gets to about 570 degrees Fahrenheit, the sensor will begin to accurately detect any oxygen in the exhaust gases and generate a DC voltage. When the O2 voltage is above 0.45 volts DC, the ECU considers the mixture too rich and will trim or reduce the injector duration a few milliseconds, wanting to see the voltage go down. When the new, slightly leaner air-fuel mixture contacts the O2 sensor, the voltage drops below 0.45 volts, and the ECU now determines the mixture is too lean. When the unit is in closed-loop mode, we should see the voltage constantly fluctuate from about 0.8 of a volt down to 1/10 of a volt or less. This overshooting from high to low voltage continues as long as the unit is in closed-loop mode, about 5 to 8 times a second. So the average voltage over a period of time works out to be right at the target of 0.45 volts. Now, your volt-ohm meter may not change readings as fast as the O2 sensor changes, 5 to 8 times a second. All you need to see is the voltage continually fluctuate between about 1/10 and 0.8 of a volt. It's critical to know when a unit is supposed to be in closed-loop mode to accurately check the O2 sensor. If you measure the sensor's output voltage when it's in open-loop mode, you could misdiagnose a rich condition or failure in the O2 sensor circuit. You could also mistake normal O2 sensor wear for some type of failure or circuit problem. O2 sensors are a wear item and need to be replaced if the output voltage never gets above 0.45 volts DC. If the output voltage never gets above 0.45 volts, the ECU will continuously try to richen the air-fuel ratio up to a certain limit to try to make the voltage increase, so the customer's gas mileage will be reduced. Normal O2 sensor wear takes many thousands of miles and possibly years, so the customer may not notice that their gas mileage average has dropped unless they keep very detailed records. Here's an easy test for all closed-loop models to see if the O2 sensor is working properly. Make a parallel connection to the 2 wires for the O2 sensor, set your volt-ohm meter to DC volts and start the engine. Let the engine idle to get the O2 sensor and engine up to operating temperature. These units will go into closed-loop mode at idle, so you should see the voltage continuously fluctuate between 1/10 of a volt to 0.8 of a volt. If you see this fluctuation, then the sensor is good and you're done. Currently, all other models with an O2 sensor have an air injection system, so the voltage will be very low and steady at idle. Accelerate the engine slowly, but keep turning the throttle to simulate acceleration. You should see the voltage spike to at least 0.6 to 0.7 volts. Non-heated O2 sensors will take some time to get up to operating temperature, so be patient and use some cooling fans on the engine. This spike in voltage is due to the acceleration compensation, a very rich air-fuel mixture to help the engine build the power needed to accelerate. If the voltage never goes above 0.45 volts, then the O2 sensor needs replacement. Keep in mind that it's the extra gas injected during acceleration that makes the O2 sensor voltage go up. If the unit has an acceleration performance complaint and you don't see the voltage spike when you accelerate, there could possibly be some issue with the injectors, fuel pressure, or one of the sensors. One last thing about O2 sensors. Engine coolant or an excessive amount of engine oil in the exhaust system will damage an O2 sensor, basically coating the O2 sensor element so it can no longer accurately detect the amount of oxygen in the exhaust gases. So if you're working on a unit that has had some type of major engine failure, like a head gasket failure, where some engine coolant has got into the exhaust system, the O2 sensor could need replacement as well. The 3-wire sensor group includes the throttle position sensor on non-YCCT models, the lean angle sensor, cylinder identification sensor, atmospheric and intake pressure sensors, and the speed sensor on most non-ABS models. The position sensor in the X-up servo motor assembly can also be considered a 3-wire sensor for troubleshooting purposes. The procedures in the appropriate service manual are generally very good at testing the particular component itself, but again, the part that the service manual is missing is checking the reference voltage. Similar to the 2-wire sensors, 3-wire sensors also operate on a 5-volt DC reference voltage, but it's a little different type of system. The ECU supplies a consistent 5 volts DC on one of the 3 wires, another wire is the ground wire, and the third wire is the signal voltage back to the ECU. Virtually all 3-wire fuel injection sensors on all motorcycle, scooter, ATV, snowmobile, and side-by-side models are connected like this intake pressure sensor. The 5-volt reference voltage flows to the sensor on a solid medium blue wire, and the sensor is connected to the common fuel injection component ground circuit with the black with the blue trace wire. And the third wire will be a unique color code wire for each sensor, which sends the signal voltage from the sensor back to the ECU. When you have a suspected problem with a fuel injection sensor or circuit, the first step should be to check for 5 volts DC on the blue and black-blue wires with the key on. If that voltage is correct, you can then proceed to testing the sensor itself and for proper continuity and resistance on the third signal wire. The 4-wire throttle position sensor and accelerator position sensor on YCCT models are tested virtually the same as a 3-wire sensor. Verify the 5 volts DC going to the sensor first. Most models, the wire codes are blue and black-blue, just like the 3-wire sensors. But be sure to verify the color codes in the appropriate service manual first. The new VMAX, for example, has different color code wires. If the sensors have the correct voltage, then verify the proper continuity and resistance on the 2 signal wires back to the ECU. And finally, check the resistance of the 2 circuits inside the sensors. So you can see that most fuel injection troubleshooting is really just electrical system troubleshooting. So all the same rules apply. Checking the input voltage to a component, making sure it has a good ground, and checking continuity and resistance in the circuits and so on. For a detailed look at each of the diag codes, what the numbers mean, and how to interpret the information, refer to the Yamaha Fuel Injection Systems book, which is also available in the tech library of YDS. Whenever you have a fuel injection system failure or a running performance complaint, take a few moments and go through the diag mode as your first step. Even if there are no fault codes, but the customer has some type of running performance complaint, it's especially important to look closely at each diag code and determine if the readings seem correct or not. So now you have a good idea of the basic troubleshooting steps. Be sure to take some time to get familiar with the diagnostic capabilities on Yamaha fuel-injected models and stay up to date on the features of new models as they're introduced. Thanks for watching.